Now let's move on to the next segment. So regarding logical connectors, we can represent them in another way. So logical, we can represent them in a tree form. Like this. Let's say that, for example, we have the following formula. Let's say that we have this formula which equates P intersect with Q implication R. Sorry, I had a sneeze there. So now I'm gonna have to end this whole thing. Actually, let me rewrite this thing. So, oh, I could actually just move it. Forgive me just 1 second. We humans, we aren't perfect, but we should aspire to be. Okay, and the whole thing implies it has to be something complex like this. That's the whole point of having a tree form. The whole point of putting it in tree form. So disjunction with the negation of R. Okay, so let's say we have something complicated like this. How do we go about solving it in a less than neuronically brutalized fashion? So what we can do is we can represent this formula in a tree form. How do we do that? Well, the first thing we do is we find the most isolated piece of logical connector. Like, say this one, for example, it's connecting two large pieces, right? So let's put that one in the middle. It may not serve as the first try, but it's fine. Yeah, we have to start from somewhere, and this is acceptable. It's perfect. It's intended actually. So let's put that one. Oh, I forget my clumsiness. Let's put that in the middle. That to be a tree. Okay. What do we have next? So next we have so we have to make a punctual separation. We have already demarked this. Now we have a disjunction here, and ideally we want to interpret this as a negation of R, so we could put it in parentheses and evaluate the next smallest subcomponent. So in this case it will be for this piece, right? Whoops. There I go again, being clumsy. So for this piece of logic on the left side we have a couple of operations, but the one that is interconnecting in a higher superposition is this one, right? So we'll grab that conjunction and we'll put it right here. And the same thing goes for the other side. So we have this disjunction and I'll put it right here. Next we'll subdivide this these two pieces, right? Because each of them, each of these connectors, let's say this one, is connecting this one and this one, right? So we will write P, which is that one, and on the other side we have this logical connector, so we'll keep ramifying that. I'll say an implication and we'll ramify it, branchify it, I mean, and put then the logical, the variables or the terms inside. This is an R. God, Gotta be careful. This is an arm. And then we do the same thing on the other side. So in here we have a disjunction, which we've already written in a crude manner. I need to be punished severely for this. Okay, so P, until I learn the ways. And then we have a simple negation. We have to follow the procedure, right? And we have a negation on the other side. And this leads to the R. Now, the beautiful thing about this is we can focus on, I mean, we could do the same here, right? But this is just a different form of viewing it. And it's a very useful tool for when these things expand. So let's say that we can have a big expression like this one, right? But instead of these variables, we have other big expressions compounded into formulas like these ones, right? These can be the variables that go on in here. And that would be like a huge, much more complicated expression, which is made abstract by compounding those smaller pieces and hiding them behind these variables. And so we can derationalize it a little bit and do it like this. So how do we do this, right? So let's say that the evaluation of Q. So let's say that this is 1 and R is, and the valuation of R is 0. Then from the table that we've studied way back, where is it? Here. So we can see that the implication for 0 and 1 over here, leads to a 1. So, and this is because the implication, when we have a 0 as the implicator, it matters not what we have in the y or in the implicatee position, it will always default to 0. It is of no consequence, right? So of no logical consequence. So in this case, this implication, this will result. Let me just create some space. Sorry. This will result in a 1, right? Because it was a 0 and a 1. 0 and a 1, 0 implied 1, it matters not, so the result by default is 1. So this one is equal to 1, right? And we can move on to the next one. Let's say that P, right, just for example, for sake of example, P is 1 as well. Then we can grab this bigger piece and we say, hey, this is a conjunction, right? Well, how did the conjunctions behave? Well, it's like an AND, right? So both of them have to be 1 in order for the result to be 1. So we go back to our initial position. So both of them are 1. So the result is 1. Next, we can evaluate the second part. So what did we say that R was? We said that R was 1 and Q was 0, right? Shouldn't have erased that, but hey. So if R is 1, then the negation, correct, this will result in 0. Now P is 1. Whoops. So now we grab the whole thing and we say that, well, so 1 disjunction 0, and how did those behave? So if we have a 1 in X and the 0 and y, then it translates to a 0. So sorry, the disjunction, not the implication. If we have a 1 and a 0, then it becomes a 1. Yep. Why? Well, because it's an OR, so it only evaluates to 0 if neither of either group is true or positive or 1. So this will, since 1 is since 1 conforms to the requirement of the disjunction, which is either one of them has to be 1 in order to result in true or 1, then the result will be 1. Now, let's evaluate the whole set. Right, okay, so this set resulted in 1 over here, and this set resulted in 1. So what do we know about implication? What will this surmount to? So an implication, if x is 1 and if y is 1, what happens? It so happens that x enables y to be whatever to become the result of the set. So if x is 1, then the result will be whatever is contained in y. Otherwise, the result will be 0. So in this case, since y is 1 and x enables y, we will get the output of 1. Now, let me clarify something just for future people filled with malice that may try to confuse you. There are people that will try to say that, you know, the formula, okay, let's say that this formula P, yeah, and this formula, they will try to confuse you by asking, is this formula equal to this formula? The answer will not shock you, but it will put you in inquisitive mode. What is the answer to this? Well, there is one simple answer. The answer is no. Tell those people that they're trying to mess with you and that's okay. Let me default back to the teacher mode. So this is not the same formula, but the valoration of this is the same as the valoration of this formula, of the psi. Yeah, I figured out the name of this symbol. This is the psi, and this is the phi, or phi, from Phil. Yeah, because so the symbols matter in the formula, right? Not in the valoration. So this is the value that we obtained, and from this, and this is the conjunction, so the formula and the valoration. So the formula defines also the operators that it contains. The valoration contains the resulting set only. Right, okay. So that out of the way.